Stream temperature responses to clear-cut logging in British Columbia. The moderating effects of groundwater and headwater lakes.
Why was this studied? Stream temperature is one of the most important factors in determining the quality of aquatic ecosystems. Streamside timber harvesting increases the exposure of a stream to direct solar radiation, often resulting in increased maximum temperatures and diurnal fluctuations. This can negatively influence aquatic ecosystems, so the process of warming and how much warming occurs are important factors to understand.
The research objective. The main objective of this study is to investigate how streams headed by lakes change temperature differently than headwater systems. To do this, the authors examined the temperature patterns of two small lake-headed streams using a case study approach. The hypothesis tested was that lake-headed streams would not show the same degree of warming following streamside harvest as previously reported for headwater systems.
The study location. The case study focused on three small, lake-headed, forested streams located in the subboreal spruce biogeoclimatic zone of north-central BC, as shown on the map, just north of Prince George. The streams are small, with less than 2-meter bankful widths and low gradients of less than 4%. Each stream was headed by a small, relatively shallow lake with an area less than 20 hectares.
Method. To evaluate warming, temperature monitors were installed at the upstream and downstream boundaries of each stream study reach, and hourly stream temperatures were recorded. The authors examined the temperature patterns for 1 year before and 3 years after clear-cut logging.
Two study streams were then subjected to streamside timber harvesting in February 1998. One stream was not harvested to serve as a control. Timber harvesting within the 30-meter riparian zones of the study streams consisted of clear-cut logging that removed only mature commercial timber. Before harvesting, all streams cooled from the upstream to downstream boundaries, which is a result of cold groundwater recharge.
The two harvested streams continued to cool during the 3 summers following logging, even though 50% of the streamside vegetation was removed. In Stream 16, cooling during the month of August increased by an average of approximately 0.5 Celsius in 1998, and 2000 increased by approximately 0.4 Celsius in 1999 relative to the 1997 trends. In Stream 48, cooling in August decreased by an average of approximately 0.5 Celsius in the first 2 years following logging, but then remained relatively unchanged in the year 2000. For the unharvested stream hip, temperature was relatively unchanged.
These results confirm the hypothesis that after timber harvesting, lake-headed streams experience less warming than headwater streams. Previous studies showed headwater streams increased average temperatures by about 5 degrees Celsius and diurnal fluctuation by 6.6 degrees Celsius. By contrast, max and min temperatures of the two treatment streams increased and decreased by a net average of 0.4 degrees Celsius, while diurnal fluctuations increased by a net average of 1.1 degrees Celsius.
Why this research is important. Most studies investigating the impacts of streamside harvesting have focused on headwater streams. However, much of the future timber supply in the northern hemisphere is expected to come from forests in temperate, interior regions with moderate gradient and low precipitation rates. We should prepare for this future by learning as much as we can about these stream systems.